Folks, in the past 2 months, I have done about 14 or 15 video segments on the use of the Catia's native FEA solver to analyze composite problems in Catia. All of these have been done either with the V5-6, Catia version 5.6, release 2016, and a few of them have been done with release 21, which is roughly 9 years old. I've noticed that although all of these versions up until the most recent one, which is I think 2018 or 2019, although they give the same deflection and in many cases, in all pretty much all cases, the same von Mises stress, but the display and calculation of the components of stress in different scenarios, such as fiber and transverse direction, or perhaps local coordinate system of the shell, etc., they're different. And the most recent version that I have access to, which is R2018, many of these bugs have been fixed. Okay, so from now on, I'm going to be using R2018. Okay, now if you're using earlier versions, the process works, and you're going to get numbers, but you've got to be very careful when you look at the plots, the contours of the stress components, okay? Although deflection and, as I said, von Mises stress, in all likelihood, will be the same. Okay, the next two videos, this one and the one that's coming up next, they are going to be dealing with thermal stresses. In other words, we don't have a mechanical load, and all we've got is the composite, the laminate, subjected to a thermal load. Obviously, if you know how to do this, if on top of this thermal load you have a mechanical load, it's just a matter of applying force or pressure or whatever it is that you have. Okay, so let's concentrate on this very simple problem. Let me put this thing in the slideshow mode. There we are. Okay, so the problem that we're going to be looking at is this good old rectangular strip of 4 by 1 inches. Okay, and this has a ply thickness. It's made of carbon epoxy, and it's got a ply thickness of 0.01, and there's 6 of them, as you'll see. Now, this composite is formed. The layup has been made, and you take it and put it in an oven, which is 202 degrees Fahrenheit. Okay, so you let it basically raise the temperature up to 2020 Fahrenheit, which is the cure temperature for carbon epoxy. And once it reaches there, it solidifies. At that state, right before it reaches 2020, right before that, it's got zero stress in it. And you take it out of the oven and you let it cool down in the room temperature, which is 70 degrees. Therefore, there's a temperature drop of 150 degrees. What we want to know is what are the locked-in stresses in that composite, or what is called residual stresses, in that composite when it's taken from the oven and brought into the room temperature. Okay. All right. So the 6 plies that I'm going to be doing are like that, and this is both a symmetric about the middle reference plane and balanced. Okay. So after deformation, after it cools down, this thing is not going to warp. It just shrinks. Okay. So now, the data that I'm going to be taking, along with the hand calculation that I'm going to be presenting for comparison purposes, are taken out of this reference at East Carolina University. And these are the numbers that this fellow is using. The only thing is that the coefficient of thermal expansion in the fiber direction, in the longitudinal direction, is negative, taken to be negative. Catia, I tried, it will not take negative coefficient of thermal expansion. But this is a very small number compared to alpha 2. Notice that it's about 100 times smaller Therefore, what I'm going to do is I'm going to assume this is 0. So I'll set alpha 1 equal to 0 and then run the problem. Now, my spreadsheet, which basically replicates the work of this fellow up here, of course, all I have to do is to set alpha 1 equal to 0 here. So the stresses computed are slightly different from this gentleman, William Howard, has, because we have slightly different coefficient of thermal expansion. But they're within 10 psi of each other. So now, as I said, I can't use this, so I'm going to take alpha 1 equal to 0. And notice that you're going to have to specify the coefficient alpha 1 and alpha 2 in the composite table, except that the unit there for alpha 1 and alpha 2 is per degree Kelvin. And I could not change the unit of that thing to 1/degree Fahrenheit. So what I have to do manually, I have to take this 15.6 and multiply it by 9/5, which is coming from conversion from centigrade to Celsius to Fahrenheit, which is a factor of 1.8, by the way, and you're gonna get this. So this is the number that I'm gonna put in the table of material properties. Okay, not 1/degree Fahrenheit. Okay, so that's what I'm going to put in there. Now, these are the reference values that I'm going to be comparing it. So for the 30-degree plies, I have one meso stress. I have the coordinate system along the fibrous and transverse direction, and these are the local stresses for 30-degree ply, minus 30-degree ply, and 0 ply. And I'm going to be comparing my numbers against these. Once again, I mentioned that if I use other versions of Catia, even as recent as 2016, the von Mises stresses are going to be okay. But when it comes to matching these numbers, they don't write. I believe there was a bug there that they must have fixed. Okay, so this was done with 2018. Minor changes, you can run it. However, be aware of the fact that displacement and von Mises stress may match, but uh, the, 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 the matching of the components of stress is going to really confuse you, because they're all mixed up in the older versions. But 2018 uh, seems to have been fixed in that version. Okay, so I'll keep this thing here handy because you're going to need it later on. All right, so let's start with our Catia program. And the first thing I'm going to do is I'm going to create my material properties. So I go to Start, Infrastructure, Material Library, because I have to make it. So double click on this and start making it. So I'm going to call this thing January 1, 2021. Okay, and notice that the name changes here. Okay, so composite, unidirectional ply, unidirectional fiber, and the only thing that I have to input is the cute thickness is 0.01. Okay, that was my assumption. Notice that there it was, 0.1 inch. Okay, and apply. Then I go to analysis, make it 2D orthotropic, and putting my properties. So this one is 20 million, 20 e to the 6. This one is 1.2 million, 1.2 e to the 6. Poisson ratio 0.25. I just noticed something, 0.25. I just noticed that here inadvertently I put down 1. It should have been 1.2. 1.2. Okay, good. Shear modulus 800,000 in the XY plane, 800,000. In the other two planes, 400,000. 1, 2, 3, 4, 5. And 1, 1, 2, 3, 4, 5. Oops, 40,000. 4, 1, 2, 3, 4, 5. Okay, good, good. Now, if you look at the thermal expansion here, there's two of them. Longitudinal thermal expansion that we agreed, I'm going to make it 0 because we won't take the negative number. For this one, I already made the conversion in that, in here, I made the conversion. It is 2.808, 10 to the minus 5. So let's put it in right there. So 2.808 e to the minus 5. As I said, generally speaking, you can change the units to what you want, but I could not find a place where coefficient of thermal expansion could be changed from K degrees Kelvin. Okay, I don't think we need anything else, so we just apply and we just say okay. Let's double check this again. Analysis, numbers are there. Okay, and now we're going to save it. Save it in the on the desktop. On the desktop, I'm going to make a new folder. So here I'm going to put my first thermal video. Okay, we're going to put it there. And the name of the material database, why don't I just leave it like this, but I'll just tag on something at the end so that I know what it is. So I'll say, how about material 1, how about January 1? January 1, okay? Say okay, and we can close this. Notice that on my desktop, there is a folder here, and that got, oh, where did it go? Okay, right there. I forgot to put this thing in that. Right there. Okay. If you double click on this thing opens up. You can check it out. Everything is good. We close it, and now we're going to create our part. So we start with a part file. Okay. We go to generative shape design. Okay, there we are, because we're going to create a surface, so that's where you need to do it. Immediately, I'm going to save my file. So File, Save Management, Save As. This is the right folder, my first thermal video. Okay, so part 1 is going to go in there, and we're going to make it. So on a convenient plane, on the XY plane, we'll sketch a 4 by 1 rectangle, 4 inch by 1 inch rectangle. So this is 4 inches, and over here is 1 inch. Exit, fillet, F-I-L-L, right there, fill, F-I-L-L, so it puts a surface on that rectangle, and I'm going to join it. And as I said, the reason I join these things is that once you join, the surface will have a direction determined by this arrow, and eventually when you mesh this thing with shell elements, it has a normal. The direction of the normal to the shell element is going to be opposite to this. So I flip this thing down so that I know for sure that my normal to the shell element is going to be upward. Okay. It really doesn't matter in these problems, but it's important to have a control over some of the stuff so that you know how it's going to turn out. Now, this is pretty much done. So let's see here. Now, while I'm there, I'm going to create 3 coordinate systems. One of them is my rosette, which is aligned with the global XYZ system. So let's see now. Where's the coordinate system here, or axis system? It's right there. There's the axis system. You click on it. By default, it creates that coordinate system with the origin at the global origin. I don't want that. I want to move this thing a little bit to the left. So I'm going to give it a y of -1. So I'm going to put it right there. And there's the coordinate system. This is going to be used as my rosette. So these angles are going to be specified with respect to the x-axis of this rosette. Now, also, I uncheck the current so that my current coordinate system is always the global one. Okay, let's do another one. Now, for point, create a point. It's the same y, but for x, I'm going to make it 2. So I'm going to create my coordinate system there, but I'm going to rotate this thing about z-axis by 30 degrees. And the reason I rotate it, because I want to show you, to get the stresses in the fiber and transverse direction, you have to use the right coordinate system, which is 30 degrees, so that it is aligned with the fiber direction. 30 degrees. Some other software such as Abacus and ANSYS will do that automatically for you. They automatically plot the stuff in the correct or in the desired direction, but I don't think Catia will do that. Okay, there, 30 degrees. And then do another one, except at minus 30 degrees. Well, those are for the minus 30 degree plies. So another one, where is it? Right here. And we're going to move this thing by another 2 inches, so make it 4. So it's going to put it right there. And I'm going to rotate about Z minus 30 degrees. Minus 30. Okay, good. Now, since I don't want to get confused here, I'm going to give these things proper names. So the first one is going to be the rosette, which incidentally is it's aligned with the global XYZ. This one I'm going to call rotated by 30. Rotated about Z. This is global Z by plus 30. Okay. And then the other one, properties, is going to be rotated about big Z by minus 30. Okay. Perfect. All right. So we're done here. Now we're going to go to composite design because we want to create our um, uh, plies and things like that. So the first thing that you need to do is composite parameters. Add the material. Remember, I created that database that I'm going to be using now. So it was on the desktop, and it was called It was called my first my first thermal video. This is the database that I created. There we are. The name of that material was January 1, 2021. Hopefully, it's going to be a better year. And for laminate, for rosette, the rosette is going to be add a rosette, and you select this one that's global, lined up with the global one. I'm going to hide this. Okay, so this is perfect. And for directions, 30 and minus 30 is not one of the default ones, so add. I'm going to call it plus 30, and the value of it, that's just the name by the way, is 30 degrees. And the color of it, I'm going to change to something else. And then I'm going to add another one. I'm going to call it minus 30, and the value of it is going to be minus 30 numerically, and the color I'm going to change it to dark brown. We say OK. So we have these two new directions that we added. There's nothing else we need to do here. We say OK. Let's save everything. OK. Now, there's 6 plies here, so it may be more efficient. It may be more efficient if we created a zone and then created the plies based on zone. And there's nothing wrong with that, except that when you create plies based on zone, you're gonna have to check. You're gonna have to check the angles, make sure that in the proper stacking sequence, and you change it if necessary. Because when you create the plies based on zone, it will create the plies, but the angles are not necessarily in the stack that we want. So rather doing that, I'm going to create it manually. So I'm going to say, okay, let's do a pile group. Okay, and the surface is right there. This is the surface. The draping direction, I'm going to make it upward. But in this particular problem, it really doesn't matter because I'm going to place the entire stack symmetrically about this reference plane and lock the plies draping direction. Fine, that's fine. Very good. So now we're going to start creating our plies. So first ply right there, ply. In that ply group, the contour of it is that sketch. That sketch is very convenient, as you can see. And the material is correctly selected, but the first ply is my plus 30. Okay? And repeat this thing 6 times with different angles. So the alternative is do a cut and copy and paste 6 times, and then you have to fix the angles one by one. So, but it's just as easy if I did it like this: ply in that ply group, contour is that sketch, attribute, the direction is -30. Okay, again, in that ply group, the contour or curve is that sketch. This one is 0 degrees. Okay, next one is also 0 in that group. The sketch is the boundary, and this is also 0, so we don't have to change it. Fifth one is -30. The contour is that sketch, and this is -30. And the last one is +30. In that group, contour is right there, and attribute is +30. Okay, very good. Save everything. If you want to see them, you want to display that here, right here. You can see this is the ply exploder. Select the plies group and say apply. So you can see that +30, -30, 0, 0, plus -30, +30. Cancel that because I don't need it. Very good. We're done here. So now we're going to go to mesh this thing. So we go to Advanced Meshing Tools, Surface Mesher. That surface, I'm going to measure it with 0.125 inches, okay, 0.12 parabolic, and zap it or mesh it right there, mesh it, and we say okay, and we exit. We're done here, so we're going to go to Generative Structure Analysis. Let's look at our mesh, make sure it's the right size as far as the look is concerned. Change the rendering here to with edges, so 0.1215 is roughly these things, okay? Notice that 0.1255 times h is going to give you 1 inch, which is the width of this. Okay, good. Let's deactivate this. Deactivate this mesh. Very good. Now we're going to go and create our import our properties, import our composite properties. So there it is. Notice that for regular shell, you need the thickness. For composite shell, you have to import the composite properties. So the support is that surface, the joint, and we did it by plies, so we're gonna have to select the plies group. So you go to the tree, expand it, expand it. There's your ply group. If you want to exclude, if you want to exclude some stuff, you can go and select it ply by ply. But in my case, I don't want to exclude anything. So so there we are, and it's symmetrically located about this reference plate. In other words, 3 plies down, 3 plies up. Okay, very good. Incidentally, if you want to do a little bit of fancy stuff here, you can actually do some plots here if you want. So you put the property, right click. Okay, so to do that fancy stuff, the first thing that you notice that I haven't specified my thermal load or things like that, but you can make a run here and just say, show me the mesh only. You have to do this if you want to do that fancy stuff. So you put the cursor on the properties and you say generate image. For example, show me the thickness. How about the thickness? So fringe thickness. Notice that it's 0.06. There is 6 of them, right? 6.01 times 0.01 is 0.06. Let's do another one. For example, show me the angle in each ply. So composite angle. Okay, now to see it better, you bring the part in hiding, from hiding. You can see it there. So if you double click on this thing that you just did in the properties right there, you can select it lamina by lamina or ply by ply. So lamina, so this one was 30, then it's going to be -30, then it's going to be 0, and then 0, -30, and 30. So these are okay. These are some stuff that's good for debugging and things like that. So I'm just going to deactivate it. Okay, now as far as the load is concerned, the only load on this is thermal load, which is 70 degrees. So the first thing that we're going to do is this is the temperature field. You click on it, you select the surface, and you put 70 degrees on it. The only thing is that you have to say, what is the reference temperature? Remember, reference temperature is ordinarily room temperature, but not in this problem. In this problem, reference temperature is the curing temperature, which is 220 degrees, at which the stresses in the composite was 0. So we say, okay, now how do we set that? Notice that as soon as I click on that thermal right there, as soon as I did this load, it put an extra line here which says environment. This was not here before until I touched the temperature field. Over here, I touched the temperature field, I brought it up, and then this thing lined up. You double click on it, and this is where you specify the reference temperature. Notice that the default is 68 degrees Fahrenheit, which is the room temperature roughly. So we're going to make 220. So I'm assuming that room temperature is 70 degrees. So 150 plus 70 is 220. We say okay. And now I can run this thing. The only thing that is going to bomb out because nothing is constraining this thing. Nothing is constraining this. This is just floating in space. So I can apply the 1, 2, 3 rule, or I can apply the isostatic restraint right there. You see this? You recognize that these guys? This is for the 1, 2, 3 rule that we did in the earlier videos. This is for isostatic. In other words, automatic imposition of the 1, 2, 3 rule. Remove rigid body motion. Notice that I don't select anything. As soon as I click on this, it actually puts an anchor on this. So now everything is set, and we're going to save this thing, file, save management. This analysis I'm going to save in that same folder with the same name. So in this folder, right now I have the material database and I have part, and now I have the analysis. Okay, we're going to run it. Always pray. Always pray. Make sure you don't have mesh only. Change it to all, okay? Good. Okay. Your praying helps. All right, so let's plot the deformation displacement. There we are. Now let's change the scale colors here. So we go to visual, average ISO, change the rendering to material. So it's like that. Look at the view from the top. View from the top. It's the top view. Notice that all it happened is that it stretched, okay? And there is no shearing here. It did stretch, okay? So if you want to see how it compares with the original thing, so bring this thing out of hiding. There we are. Actually, this is not stretching. This is shrinking. This shrinks. So it shrunk. Okay, I suppose must have shrunk. Okay, very good. Now, there's a couple of things you can do. First of all, you double click on this contour that you plotted, uh, and you can say, don't show me the deformed shape. Show me the displacement on the undeformed shape. So this matches the undeformed shape. Okay, so that's up to you what you want to do. Let's go ahead and plot the stresses. Okay, so deactivate this. To plot stresses, remember you have to put the cursor on static solution case, right click, generate image, filter it according to stress so they can find it very easily, full tensor component. Now, why don't we make a box here so that these end effects are not shown? These are the end effects. Okay, so what we're going to do is, let me deactivate that. Let me create a box here, a box group. Where's the box group? Right there. So there's the group. So there's the box group. It makes a big box here, and I can resize it, change it, etc. The reason it looks nice right now in the middle of that because I already created it in an earlier run. So let me resize it, etc. You click on this box, and then you can resize it, etc. For example, I can grab these ends. Well, first of all, zoom out. Okay, so you can grab these ends and make it smaller, shrink it in this direction, in that direction. If you want to shrink it in this direction, you can go as far as you want. I'll leave it like this. So it's just that strip, okay? Very good. Now, hide the box, and activate this contour that you created. Okay, but look, I don't want to see the entire thing, so we say selection. Just show me the stuff inside of the box. Double click on it. There we are. Stuff inside of the box. So what exactly is this? Well, we want to show the one Mises. We want to start with one Mises. So don't worry about the tensor component. Go with the one Mises. Layer 1, one Mises, 5,220. Okay? Layer 1, which is 30-degree ply, one Mises, 5,220. Hallelujah. Okay. Let's go to layer 2. Layer 2, one Mises, 5,220. There we are. Layer 2, which is minus 30-degree ply, same thing. Here's your layer 3. Let's go check the layer 3. Layer 3, one Mises, 2,890. 2,809. So the one Mises stress matches. Now let's go and apply the let's check the stresses in the local direction. Now when you say local means in direction of the rosette, local means it's referring to local, it's referring to the local shell element direction, which happens to be aligned with the rosette also. It is also aligned with the global one. And if you wonder, I'll show you in a minute why am I saying this thing. But let's see if we can get these numbers. Okay, so we go here and say, all right, I don't want to see the one Mises. You can do it as a separate plot, or you can actually go ahead and select it here. Let me do it as a separate plot. So put the cursor there, right click, generate image, uh, uh, filter it by stress. There we are. Okay, now double click on it. Don't show me everything, just show me the box. There we are. And what exactly is this that I'm getting? Well, it's a local direction, lamina 1 in C11, and that means sigma x, minus 1,650. There it is, minus 1,650. Look at C22, which was sigma y, minus 642, minus 642. Look at the shear, C12, that means tau xy, minus 2,900. What is that? Minus 2,900. Now, if you do this thing with other releases of Catia, earlier version, you might get these numbers. You may not, because there were bugs. There were bugs in some of the earlier version as far as displaying these numbers, but these may be either all multiplied by a minus or etc. But it's okay. It's getting the right stuff here anyways. Now, let's do the global. You'll see that there is absolutely no difference between local and global. Notice that when I do that, these numbers don't change. In fact, if you go on C11, C22, C12. And I'll come to that in a minute. Why is it that the local and global directions are going to give you the same uh, stresses? We'll come to that in a minute. Now, if you want to get the stuff along the ply, along the fiber direction, in lamina 1, for example, the fiber direction was 30 degrees with respect to x. So what I need to do is to go here. Where's that? Say, okay, I don't want global or local, I want a user. And my user is going to be, oops, I have to select it. My user is going to be the one that I created here, and it was rotated by 30 degrees. As a matter of fact, if you say show me everything, you can also see it on the screen. Okay, so this is the one that I rotated by 30 degrees. Okay, so show me the stresses in a coordinate system which is like this. In other words, the x is along the fiber. You say okay, and this one is C11, negative 3,900, negative 3,900. If you look at C22, 1,610 or something like that, 1,610 right there. And if you look at C12, minus 1,010, so minus 1,010 or 11. Now, this will not happen in the other releases. As you go to other releases, earlier releases, some of them you may get numbers, but they're all mishmashed and they don't match the analytical solution. Why don't we go and look at ply number three? Ply number three. So if you want ply number two, now of course for ply number two, this coordinate system is nonsense. So we go and select the one that was minus 30 degrees. So we say okay. So for C11, ply number two, C11 minus 3,910 right there. Okay. And for C22, 1,610, 15 year. And for C12, which is your tau 12, it's going to be plus 1,010, which is correct even up to the sign. In other releases, the signs may switch and all kinds of things. Okay, now, why did I say here it doesn't matter whether you do local or global coordinate system? Here's what I mean. Oops. Yeah, this video is almost finished, but I want to show you that business of local versus global. Okay, so first of all, let me deactivate this. Let me deactivate that. Actually, we'll keep this here. It doesn't matter. We'll keep this thing. Let me hide this. Deactivate this plot. Okay. So let's go ahead and put the cursor on where is it? Nodes and elements, right there. Nodes and elements. Right click, generate image, and ask for local access symbol. You say okay. All right, so this shows you everything. Everything is all the elements. Show you that. Let me hide and show all the elements. It shows you all the elements. If I want, I can go only to the box. The box means the stuff in the box. So let's do that actually. So it shows you that particular box. These are the elements. There is, I think, 20 or 16 of them sitting there. But the the blue ones, you can see the blue ones, these blue ones are the direction of the shell local coordinate system. Remember, a shell in its plane has two directions, direction 1 and direction 2, okay? Notice that the direction 1 and direction 2 and direction 3 of the shell elements are all aligned with the global coordinate system. This is why when you ask for local, you get the same number as if you were asking for the global. In fact, if I had used the rosette as my global coordinate system to show me the user coordinate system, it'll give you the same as if I use rosette for that instead of the one that's rotated by plus 30 or minus 30, then you will get also the same thing. Okay. Now, these things are kind of useful because, for example, you can hide this, activate this full tensor thingy. So it shows you, oh, by the way, double click on this. You notice that these are not sitting in the same location. So you can say, don't show me the deformed one, show me the undeformed one. Okay, notice that uh, we can plot this, and you can also plot the direction of the fiber. Now I don't know which one this was. This was the ply number 2. Okay, so let me plot the fiber direction for you. Fiber direction for you. So fiber direction, you put the cursor on. Remember, we generate this plot under properties, composite angle, right there. Right click, activate, and just show me the stuff in the box. Show me the stuff in the box only. And I like to actually change the color of that arrow. Instead of this blue or purple, I want to make it red. There. So what you can see here is these are the local coordinate system for the shell element. Okay, these are the direction of the ply. Okay, ply. So this should be minus 30 if I put this thing in the ferret. Okay. So this is for which ply is this, by the way? I want to see that. This must be ply number 2. I want ply number 6. I want ply number 2, right? Yeah, minus 30 degrees. You can see that. So it helps you to debug your program. But now, I can tell you, if you go to the earlier version, 2016, one of the earlier version, these things are all screwed up. Good luck.